is it?
Oh, now it says rec.
I was just talking for now.
Now it says rec.
Compare independent states, and you measure both of them to measure correlation. Topologically,
Yeah, it's just
that should be the same and you could sort of call this the same qubit. You measure the qubit and then you compare a state. Maybe that's what's going on.
I don't know what's going on. You can, like Dan says, key exchange protocol, which looks like that. I'll send something to Bob.
Well, and that's what I think. I prefer to have then I'm doing a projection on the corresponding cube.
If you do this, then you get what they call activated one.
It's consistent. Is it positive
Why
random?
is that a name?
Well, because then the fact that you have this spatial dislocation actually guarantees some more security or something. So the whole point about Bellairs is that you can do very spatially far away things.
Okay.
So that it's far out of each other's life and then you make research. And of course you can do this.
So this talk is about quantum gravity. And what I'm going to do is and maybe you can also be quiet. So what I'm going to do is introduce what I call the causaloid framework. So that's a new word that I made up. And currently, if you Google it, you'll only find references to places where I used it. Apart from one exception, which is where somebody wanted to date causaloids. I think they meant Caucasians, but yeah. So let me start with what I think the problem of quantum gravity is. So I think the problem of quantum gravity is to find a physical theory, a more fundamental physical theory, that reduces inappropriate limits to quantum theory on the one hand and general relativity on the other hand. So we have quantum gravity here, it's a more fundamental theory, and inappropriate limits reduces to general relativity and quantum theory. So this doesn't mean, in particular, this means that quantum gravity may be something which is deeper and different from quantum theory. But many of the approaches to quantum gravity assume that quantum gravity will be formulated within the framework of quantum theory, whereas we don't want to assume that. Okay. So yesterday I learned from Bob again about category theory. And there's things, monoidal categories. And so I learned yesterday that we have things like this. We have systems, we have processes, we have tensoring and composition. And I suddenly realized yesterday that I like this. And the reason I like it is because it's more or less precisely and exactly what I'm against. At least so far as quantum gravity is concerned. I mean, I think it's great within quantum information, quantum computing and so on. But so far as quantum gravity is concerned, these four symbols represent exactly what I'm against. And I'll explain why shortly.
Oh, but that's easy to talk.
Sorry?
That's easy.
Oh, I mean, I should say actually, when I say I'm against this, I'm against the the physical interpretation that's given of this. So this is being interpreted as a system, for example, a qubit. This is interpreted as a process that happens on a system in time. This is interpreted as a kind of a way of putting systems together in a space-like sense. This is interpreted as composition in the sense of two sequential operations on a system. So with those physical interpretations, I'm against it. Of course, the broader mathematical structure category theory, you can do anything, obviously, and I'm sure you can put the stuff that I'm going to talk about within that broader mathematical framework. But that physical interpretation. Okay.
So do you mean you're against using those as the fundamental concepts on which to build the theory?
Of quantum gravity.
Yeah.
Yeah.
So of course you admit that such things can be done, right?
Oh yeah, yeah. I mean, I think it's very beautiful about what is done with this stuff. But I think that these four symbols represent exactly the conceptual stumbling block that people have in getting to the theory of quantum gravity. And I'll explain why I think that. Precisely. Okay. So let me talk about the general approach I'm going to take. So we have these two theories, general relativity and quantum theory, and each of them has what I regard as a conservative and a radical feature when you compare them with the physical theories that came before. So in the case of general relativity, the conservative feature is that it's deterministic, whereas in the case of quantum theory, it has a radical feature that it's probabilistic. In some sense, quantum theory is inherently probabilistic. You can't write down standard quantum theory without referring to probabilities. And then the radical feature of general relativity is that the causal structure is not fixed. And conversely, the conservative feature of quantum theory is that the causal structure is fixed. So I explain in a bit more detail what I mean, especially by these two causal structure related issues. So in the case of general relativity, what you do is you solve for the metric. So if you take two space-time points that are, say, nearby, then it's only after you've solved for the metric that it's only once you know the metric that you can say whether these two space-time points are space-like or time-like or whatever. So you don't fix whether there's a space-like or time-like in advance. You only fix it after you've solved for the metric. In the case of quantum theory, the causal structure is fixed, and there's lots of ways of seeing that. So one example is that you evolve a quantum state forward in time using unitary evolution. Another example of the fixed causal structure is the following. Okay, so there's a diagram. And let's just label this. Imagine you want to take, you want to consider this pair of regions. Then the standard thing that you would do is take some sort of tensor product of appropriate operators in those two regions. And this is the mathematical object that would appear in your calculations referring to those two regions. Imagine you want to talk about these two regions. Then the mathematical object that would appear in your calculation would be something like C times B. Well, it is a matrix, it's just the direct product, otherwise it would be some kind of composition. And actually, one more example that's worth considering. What about if you consider D and B? What mathematical object appears in your calculations then? Well, people don't normally talk about that, but we can define an object if we want. We can define what I call the question mark product. And a question mark product is defined like that. And it's a linear product, and if you want, I haven't done it, if you want you can sit down and explore its properties. Perfectly well defined. And in any calculation where you're looking at these two regions, this is the object that's going to end up appearing in the calculation. So what's bad about that is that, well, each of these situations refers to a different causal situation. This is space-like separated. This is time-like, but immediately sequential. And this is time-like where there's a gap in the middle that something else might happen. So each of those situations refers to a different type of causal situation. And yet if the causal structure is non-fixed, sorry, let me say it again. Each of these situations is different. So in order to know which one of these different products to use, you have to refer to some fixed background causal structure. So if you want to know whether to use this, or this, you need to know whether the two regions have this causal situation, this one, or this one. So I think that's bad. And what I'm going to do, the framework I'm going to put forward, in a sense, you could say unifies all these different products in the context of a much more general theory. And it unifies them. I replaced them with a new product, which I call the causaloid product. It looks like that.
Could you say a bit more on why that's bad?
Yeah. Let me just take a small diversion and I'll come back to it. So, this is the diversion and I'll come back to it. So it seems to me that if we want to find a theory of quantum gravity, then it's likely that theory will have the radical properties of the two component theories, not the conservative properties. And so we're expecting to find a theory which has these two properties. Actually, I think we expect it to be even a bit more weird than that, because in quantum theory, whenever you have some quantity that can vary, then you have a situation. So, for example, the particle can go from one slit in an interferometer or another. Then you can have a situation where there's no matter of fact as to whether the particle takes one slit or the other. So, not just do we have probabilities, but we also have a kind of no matter of factness kind of superposition, if you like. So, in the case of quantum gravity, where we expect the causal structure not to be fixed. And in the case of quantum theory, we expect there to be no matter of fact. It means we expect it to actually be what you might call indefinite causal structure. So indefinite causal structure means if you pick two particular points, then even after you've solved to get the solution, the physical solution to your theory, there may still be no matter of fact as to whether this interval is space-like or time-like. Even after you've solved the equations. So that's certainly bad over here, because that means that even after you've got the solution, there still wouldn't be a sense as to which product to use. So for sure, you want to be in a situation where you're putting systems together in some way. You don't have to know whether the two regions they refer to are space-like or time-like separate. So that's why it's bad.
So, isn't it true that all this happens before we even get to quantum gravity? You consider quantum fields as space-time?
Well, quantum fields, you usually have a fixed background.
Yeah, so you can think of using the expectation value of the source for Einstein.
I mean,
That's semi-classical.
Yeah.
it's semi-classical.
It's the halfway to quantum theory.
Right, but what I'm saying is it already has all these features that he's worried about.
I think it has them, but it has them in a kind of ad hoc way. They're bootstrapped up from a sort of theory that doesn't have them, perhaps. And what I want to do is from the outset sort of say these are the kind of features we're going to have. Now let's build a framework that can accommodate them in a more natural way, and then use that framework as a framework for finding a theory of quantum gravity.
Okay.
So the idea is to find a framework that can deal with probabilistic theories that have indefinite causal structure. And this will be the causaloid framework. I mean, you can also imagine a definite causal structure in a more, in a way, you can imagine that our clocks have some errors on them, and everyone has their clocks and their rulers, and so maybe even that would have a definite causal structure. But it would be nice to sort of start with this at the beginning, and then see if we can put our theory into that. Not that I've succeeded yet. This is just a framework. Okay. So there's one more component of this approach.
So Lucien, the hope is to find a theory of, I guess, the consequences of these things, to find a theory of normal quantum mechanics, which will have this property of indefinite causal structure.
Well, no, so the hope is to find the theory of quantum gravity.
Yes,
So before you can get, I think to build a theory of quantum gravity, it's good to start out with a framework that is hospitable in the first place for that theory. So then this theory of quantum gravity will be a deeper and more fundamental theory than either quantum theory or general relativity. But then it will approximate quantum theory, and it will approximate general relativity, two domains. So it won't itself be the same as quantum theory. Look, incidentally, I can actually, in this framework, I can put quantum theory. So quantum theory is an example of a theory that has definite causal structure, but nevertheless it will fit into this framework. I haven't yet shown how to put general relativity into the framework. That's what I'm working on. Okay. I should just done general relativity on this blackboard and quantum theory on this one, because then it's like chalk and pink things. Okay. So I want to take an operational approach. So I think operationalism is appealing from the point of view of computer science. But I need to spell out how I'm going to do that a bit. So here's the idea. During the course of an experiment, you collect data, lots and lots of data. And I'm going to imagine that the data is collected onto cards. So here's one piece of data. Here's a card. There's three pieces. So here's one card which will have three pieces of data. I'll explain. So the first piece of data is X. And this represents something like space-time location. So whatever measurements are playing a role in giving you something like space-time location. The second piece of data is some sort of choice. So imagine, for example, you may have a spin measurement. Well, the spin measurement device will have some space-time location that you may measure off some. Maybe you may measure it using GPS coordinates or whatever. You have some way of measuring the space-time location of the spin apparatus. And then the spin apparatus will have some orientation. And again, you can choose that. So that is f sub x. So that's the choice of knob settings. And then the last piece of data that appears on the card is the outcome. So if it's a spin measurement, you'll have some outcome, like plus or minus.
So you assume you have fixed the set of observables that you can choose? The f are coming from some sort of fix?
So I'm assuming if you do an experiment, then there are sort of various devices that you can play around with and put in different places. So yeah, so it's because I'm taking an operational approach. Yeah, I'm assuming we're operating at this operational level of description. Of course, I'm not actually saying what this set is at this stage. I'm just in an abstract sense that you can choose. Yeah.
Where do you pick these space-time locations from? Because you don't want to assume a given...
So you can choose, they could be, so maybe I should give an example. What something like that. You can imagine you had a whole bunch of probes. here's a probe, and it's floating in space. And here's another probe floating in space. And then each of the probes has on it some knobs you can choose to set some instruments inside the probe. It has some meters that you can use to see what spin results you've got and so on. And it has a clock. Here's a clock. But it has a time reading, so this is probe 1, C1. And then also you can, in this example, you can look at the other probes and see what the time reading is on these probes, at this probe. So, so you get a kind of retarded time. And then in this example, your x could be the set of data T1, and then also the retarded times. The time of probe n seen from probe 1. So that would be an example of something that would play the role of x. But at this stage, I don't want to fix in advance exactly what x is going to be. I'm just going to leave it as unspecified for the time being. But something that you could use to regard as a kind of space-time location.
Could it be as little as just an arbitrary variable? Or does it need to be more?
I think so. So at this stage, I want it to be something actually referring to measurement. But I think it could ultimately be just an arbitrary label. Certainly the things I'm working on right now take it as an arbitrary label. And in the case of general relativity, that becomes an issue. You get different orders of invariance. Okay. So, so I can represent this just by a little box. So in a sense what I have is I have some x label, some knob setting, and some measurement result. So that could be my box. I can just represent that simplicity by a box like that. And then this is what I have. I collect lots of pieces of data. Okay, there's no particular ordering on these pieces of data. I just collected these cards, represented now by these boxes, lots of pieces of data. Each one has an X and some choice of knob setting and some outcome, but this is what they are. So now you can see why I think that the monoidal category approach is precisely the wrong thing. So let's just go through them again. Well, we had wires. A wire would be something like this. I don't have any wires. So this is bad. We had processes. Well, that assumes wires. So I certainly don't want the wire part of the process. We had the tensor product. Well, that assumes that two things are sort of next to each other in space, and there's not some time sequence between them, there's some lane going from one to the other. So I don't want that. Let's cross that one out. And the same remarks apply to composition. So I don't want that either.
But you mean your cards all exist if you've actually done this and you've collected your cards together, then they're there and they're sitting there on your office table, all space-like separated from one another.
Sure.
I mean, I don't think just because they look like little boxes the way you've drawn them, I mean they're all.
Yeah, but I think so. If I was to draw what these cards actually represent from the point of view of a standard quantum circuit, they might represent things like this quantum circuit. So the fact that the cards end up on the table at the same time is irrelevant. The point is, in the quantum circuit that they refer to, they're all sequential measurements. And so I don't think that matters.
Are you sort of you're identifying the card with the measurement that it represents?
Yeah. I'm saying, because I'm taking an operational approach, so I'm interested in how you correlate data. The data is taken from some real experiment, and in that real experiment there are sort of real physical things happening where you take pieces of data. So in a standard quantum circuit, that data will be collected at different times in the course of an experiment.
So if one experiment you perform is time-like separated from another, then there would be a little imaginary line you could draw in between two cards to represent the fact that one card, the data on one card was collected in a time-like fashion after data on another card, which would...
Yeah, but so anything like that, though, I would want it to be part of the data, rather than drawing some imaginary lines that are just in my head. I would want to have...
Yeah, but they are part of the data, because you're
Basically, you're
calculating them from the
constructing
data.
your category rather than assuming it.
I mean, that may be the case, I don't know.
Given all of those cards, you could say, okay, this card was collected after this card, so I'll put it on top of it. This card was collected in a space-like fashion with this other card, and you could construct...
No. So the ordering, so what's very important about the approach I'm taking is that the order of the cards, so you collect the cards in some particular order because you want to form a file, but the ordering is not important, you can shuffle them.
Yes, but then based on the data in the cards, you can recreate...
Only if you have some belief about causal structure on this X. If you don't have any belief on
How could you have recorded that X in the first place unless there was some pre-existing...
Easily, you just record an X, some data, some
But that has to mean, that's
some
that
lights,
can't, that
some-
isn't just
some
a meaning of the
lights flash.
symbol. That what you write down is just how that. What does that mean? That symbol, if you can't use it to recreate.
Well, but it sounds like you're saying is you can't have indefinite causal structure, you have to have definite causal structure, is what you're saying, it seems. Now that's patently
So
wrong.
if you have indefinite causal structure, I don't understand what the space-time location is actually referring to.
Is it just a name? Is it just a
It's
name?
just a name, it's
Just a name.
Well,
Okay.
it's just some lights that flash on your device.
It's not a space-time location, it's a space-time location.
Exactly. Some lights flash on your device, and you regard that
But
as a
then
space-time
what
location.
content is there in what you write down in that,
Well,
that
because
slot?
in
If it's just a-
an experiment where if I use this model of an experiment which I know has definite causal structure, I can use this thing I call space-time location to be, for example, the measurement of X on some fixed space-time reference frame. But it needn't be that. It could just be some other physical thing that will serve as X.
Maybe it's more interesting if you tell us what comes in place of this.
But maybe I should just progress because I think you'll see how it all works out. Okay. I mean, I think that thinking in terms of causal concepts is very ingrained into our physical theories. And so if we're going to take on a problem like having indefinite causal structure in our theories, then we have to take on those ingrained notions of thinking. And so that's what I'm trying to do. Okay. So there's a problem that crops up. So here's an example. Actually, incidentally, in answer to the question whether time is going up or across or down or to the left, or it doesn't matter in this case. But in this example, this is just an example from standard quantum theory. So let's imagine we have a source that emits a spin half particle. Then we make 3 sequential measurements of spin. And consider this quantity, probability of getting spin up in direction on the third device. Given that we got spin up on the second device, and given that we measured spin along, say, the x direction on the second device and the y direction on the third device. So there's a probability that we can think about. And that probability is equal to half. You can calculate it using quantum theory, the answer is equal to half. Here's another probability we can consider. At least I can write it down. This is the probability that we see spin up at the third device. Given that we saw spin up at the first device, and given that we measured spin along the y direction at the third device and the x direction on the first device, without saying anything about what happened in the second place. We can't use standard quantum theory to calculate this probability. And so what's the difference between these two situations? Well, the difference is to do with the causal structure. In one case, the causal structure is such that we can write down a probability, and in the other case the causal structure is such that we can't. Now, if I want to have, if I want to be able to proceed in the case where I have indefinite causal structure, I have a problem because it seems that causal structure is playing a very important role here. It's telling me what I can and can't calculate. So how do I get around that?
Is it just telling you what you can't calculate, or is it telling you what's just not well defined? I mean,
Okay, so yeah, it's telling me what is and what isn't well defined. Sure. So in quantum theory, you don't normally think to try and calculate things that aren't well defined because you have this intuition, this gut sort of knowledge about what you can and can't calculate. But you can certainly write down things that just aren't well defined within quantum theory. And one imagines just don't. There's no sense in talking about well defined values.
Is there a problem that you're also talking about seeing spin up at the third device when you're measuring signal y on the third device?
No, I don't think. I don't think so. I mean, if I put a 2 here and a 2 here, this is a perfectly sensible quantity that I can calculate in quantum theory.
I'm saying, isn't the problem not with the last observable? You have signal y and its eigenstates are not up and down. And you're saying.
Sorry. I mean, seeing spin up along the y direction.
Oh, okay.
Sorry. Yeah. So seeing spin up along the direction indicated by this label.
Yeah.
Fine. Okay. So what I propose to solve this problem is that we don't have to be referring in the usual way to some definite causal structure, but we still want to have something like the following. We want to have a two-step approach. So step one is we do some calculation. We do some mathematical calculation, and depending on that calculation, we say the property is or is not well defined. Okay, so we write down a mathematical condition, let's say. If this condition is satisfied, then the probability is well defined. And then in the case where the probability is well defined, so in the case where this mathematical condition is satisfied, then we have step 2, which is that we calculate the probability. So that would seem to be a way of coping with this problem in the context of having indefinite causal structure.
But you make it seem as if the undefinedness of this probability has something to do with the mathematical theory, but it's just undefined in the experiment. There are things you can do at 2 that lead to one probability, and there are other things you can do that lead to different probabilities. So
well,
it's not in the theory.
The theory should reflect the experimental situation.
But it's not a well-defined experiment.
Which isn't.
What I mean is, I can do one experiment where I do a certain thing at 2, and then this probability that you're done will be, for example, 1. And I can do a different experiment where this
okay, so this is a different way to say it. So what I mean by well-defined is it the case that you need extra conditioning so that you can calculate this probability or not? Okay, so there are many cases where you don't need extra conditioning. This conditioning by itself is sufficient to say the property is well-defined. So in the first example, I showed you the conditioning, as I've written it, is sufficient, but in the second example, the conditioning isn't sufficient. And so it's only if you add extra conditioning that you can make it well-defined.
So is your point that this is not a probability, but it's a function from what you can do at 2 probabilities?
Sorry,
once you fix what you do at 2, then it's well-defined. So this is like...
No, but the problem is you're thinking now, you're still thinking now in a kind of, I mean, that is true, but I want to get rid of the way, I want to get rid of thinking in this way that relies on time ordering. So if my way of thinking afterwards still relies on knowing that 2 is intermediate between 1 and 3, then I failed. So what I want to do is mathematize the role that was played by this kind of a sort of tradecraft that we have. We just happen to know because of the way physical theories work. But I want to mathematize that process.
I see. So it might be that actually 1 comes before 2, or 1 comes after 2.
Yeah. And it might also be that you have some crazy sort of situation, very, very, very complicated from your point of view, but where actually probably is well defined. So the situation looks crazy complicated from a causal point of view, but actually probably is well defined because of something inherent in the mathematics. So that would be nice to be able to mathematize that, so you don't have to think through some complicated set of through some complicated causal reasoning. Okay, I'm way over time. So let me say how this works. So I have all these boxes. And I can circle some bunch of them. Okay, here's just circled up a bunch of them. And I can regard that as a region, sort of a region of space-time. Let's call this region R1. And then in region R1, so region R1 is built up of a whole bunch of these x's. So I'll write that it's equal to it's nothing sophisticated though. So this is I'm just building up region 1 from a whole bunch of these elementary regions. Then I also have a bunch of choices that are associated with region 1, which I can just, slightly using notation, I can write it like this. That's just all the choices on the cards. And then I have also a bunch of outcomes in region 1. So we have that kind of situation. So we can imagine having region 1 and region 2, and then imagine wanting to calculate this. So this is the probability of seeing outcomes y2 in region 2, given that we saw outcomes y1 in region 1, given that we made choices f1 in region 1 and choices f2 in region 2. So that's the probability I can write down. It's like the like this in a more general sense. And so I want to have a calculus for calculating these probabilities using a two-step approach. So I'm going to jump to the answer, and then depending on how much time I have, I'll fill out where the answer comes from. Just here. Okay.
Space-time label on that.
8, of course.
No, I'm going to say 8. Actually, when I was trying to do this, I spent a lot of time staring at playing cards. So, trying to think. So in this framework, there exist vectors, which they have a sort of they're associated with any given region will have vectors like this associated with it. So region R1 has vectors like this associated with it. I'm going to go into more detail in this later, just to give you the outline. So what you can do is you can construct these two vectors, R, Y1, so there's a vector for region 1, R1 plus R2, R1 union R2. I'm assuming these two regions are disjoint. And here's another vector. I'll define the notation in a moment. So the notation here is, well, in region 2 we have a choice. The knob settings are denoted by F2. And consistent with that choice of knob settings are many different outcomes. And these are all the different outcomes that are consistent with that choice of knob settings. Okay. So now, step one. The probability is well defined if and only if these two vectors are parallel. This is parallel to this. And in the case where this condition is satisfied, we have step two. The probability is then given by the ratio of the magnitudes, the ratio of the magnitude of this one to this one.
But isn't it the two regions are parallel in the first step?
So if this vector is parallel to this vector, yeah, yeah, then the probability that we're trying, the probability here is well defined. So this is the condition that replaces thinking in any sort of detailed way about the causal structure.
I'm confused. So x is x2. This is going in what? In the set of choices.
So x2 is in the set of outcomes.
Oh, set y2. Okay.
X2, yeah. Okay. So you take the set of. So the idea is this vector is where you add of all the possible outcomes consistent with a given choice in region 2.
Are you saying something like very intuitively, like, okay, I may not know what happened there, but you know, the big superposition of all what was consistent with what could have happened there is indistinguishable from my left-hand side?
No, I think I have to show you mathematically where this comes from. It's simpler than that. At this stage, at this stage, you can't make sense of this condition. I'm just telling you the answer without telling you where it comes from. So it's just there exists this object. There's objects in this theory, in this approach, and then the well-defined condition is given is this, and then the probability is given by the ratio of this vector to that vector. And so that's how you're going to use this framework to do calculations. So
The probability of what?
Of this probability. So the thing is, this probability is a very general probability. It's not something that relies on some kind of causal structure, some known causal structure in the background. You can write down any probability of this nature, and then this framework tells you. Well, if it's well defined, and it's well defined what it's equal to. Okay.
So what do you get if you apply that to the three spin measurements that you described there?
So, and I haven't explicitly done the calculation, but in the first case, these two vectors would be parallel, and in the second case, they wouldn't. So, in the first case, they'd be parallel, and if you take the divides, if you divide the ratios, you'd get a half.
But for the second, more subtle case, it still gives no answer. It's just the same as.
Well, yes, in the second case, these two vectors wouldn't be parallel, so this condition would not be satisfied, and so you wouldn't go into step 2 because you'd know the probability was not well defined.
So this looks vaguely like a definition of conditional probability, but it's got these vectors instead of its numbers.
Yeah, I mean, it's sort of.
I mean, the ratio looks like.
Yeah, it is coming from that. Yeah, it's not. Yes.
Right, I thought
The vectors are the subtle thing.
Yeah, and it's not actually very complicated where they come from. It's just that I'm not sure I have time to get there.
I thought the point was that second experiment might have been well defined, depending on whether or not slip 3 was temporary before or after slip 2, but you weren't sure because of the indefinite causal structure.
Well, but in the particular experiment I showed you, the time ordering was very clear. And in that case, it wouldn't be well defined because you could do something in the second step to interfere. But in a more general kind of situation where you have indefinite causal structure, the kinds of situations where the probability is well defined might be more difficult to come up against. It might be rarer. So one other thing I should say is that it works out that if this condition isn't satisfied, but if the two vectors are still quite parallel, so if they're still not too far apart, then the probability will still be well defined. So the probability will still be well defined, but with some error. So there'll be some maximum amount that you can mess around with the probability, and you can start thinking about quantifying that.
Can you say again what you mean by, I don't understand this notation, this gamma underlined R1, F1, that's a vector?
So this R is meant to be, this is meant to be an R. This is a vector. Yeah, I mean I haven't defined where this comes from yet.
Oh, okay.
Yeah. I'm just trying to show you the shape of the answer before I show you how to get the answer. Yeah. Which I won't have time to do. And maybe one thing I can do is show you how the causaloid product comes in. So I mean, these vectors are essentially dual to states. That's really what they're doing. They're kind of dual vectors to states. So this vector here, you can write it down using the causaloid product. And so basically the causaloid product, what it does is it enables you to combine the vector from any two regions into a new vector. So you can see that's very much like the thing that the tensor product does and the composition and the question mark product. But it's doing it in a completely unified way. Okay, so how much time do I have?
15 minutes.
15 minutes, okay. Well, in 15 minutes I can make some progress. So I'll show you where these R vectors come from. So imagine we have some big region that I'll denote E. And then we have some region inside there, R1. So this is V minus R1. Okay. Then the probability of all the different things in here, the probability of all the different outcomes is the probability of something happening in R1, some particular thing. And the probability of some particular thing happening in the rest would be minus R1. Given certain choices in R1 and choices everywhere else. So this is really just a big joint probability that given certain choices everywhere, and then offsetting, I get certain outcomes. I've just partitioned it into two bits, one pertaining to R1 and one not. Now I want to think of this as a kind of generalized preparation. I put preparation in inverted commas because it's not as if this pertains to the past. This is just everything that happens outside of a certain region. And then this, I can think of this as a kind of measurement. In the given region. Okay. So this is a slightly odd way of thinking because normally a preparation is something that happens in the past and a measurement is something that happens in the future. But here, the preparation is something that happens everywhere else except for the place where you make the measurement.
Including possibly to the future.
Sorry?
Including possibly to the future.
Yes, yeah. So the standard thing means for standardly this could be region R, this could be region D minus R. That would be the standard situation. We can model the standard situation like this, but we can also model something much more general. And then I want to let me just reach up here. So this pair, this is the outcome in region 1, this is the choices in region 1. This sort of labels my measurement plus outcome. I want to label all of these, label all the different possible combinations like this with alpha sub 1. So alpha sub 1 will have many, this label will run over many possible values. Belonging to some set epsilon 1. Okay, so epsilon 1 is the set of all possible combinations of outcomes and measurements. So I suppose in standard quantum language, this will be a label of all the effects. So now I'm going to introduce this label up here. And call this P alpha 1. So this is the probability, given that I had measurement and outcome labeled by alpha 1, of seeing a certain joint probability, the one that's here, so given a certain generalized preparation. So now I'm going to define a notion of state. So the notion of state is that it's defined to be that thing given by some mathematical object which can be used to calculate all of this piece of alpha 1s. So the state is associated with a given preparation. And you have this long list.
Is the state of R1?
This is the state in R1, given a certain preparation in D minus R. And the next thing I want to do is something I call physical compression, which is not really related to the usual notion of compression in quantum information or information theory. And this is where I take a shorter list of these probabilities. So I have a subset of all the possible alpha labels for the omega 1 that's taken from here. And I choose this subset such that I can find a vector like this. Okay. So the point is, in general, there's a lot of quantities along here, and there's likely to be some relationships between these quantities. In particular, since there's a probability, there's likely to be linear relationships between them. So rather than writing them all down separately, it should be possible to write down a subset of them, and then use some objects that come from the physical theory to calculate all the rest of them from the state, from this object. Any questions?
You're taking a subset of them, or they just span a vector space of smaller dimension than the number of probabilities, so you just apply the interpolation.
So the way I'm thinking is that you take as small a subset as possible, and then of course you can apply the usual vector language thinking that you're talking about. But when you have to do this experimentally, you'd be testing different subsets to see which of them sufficed, so that you can calculate all the remaining probabilities for any given any preparation.
So these probably don't sum to 1.
No, they don't. These numbers do not sum to 1. And you can write down exactly this kind of thing in quantum theory, just standard quantum theory, and explicitly you can see that they don't sum to 1. Yeah. That's right.
So does alpha represent somehow what you know about the system?
Yeah, so R alpha, so what it represents, let me just, oh, sorry, let me just write this. So I'm just defining this kind of matrix to be the kth component of this vector. So this matrix really is the matrix that takes you from the smallest back to this biggest. So if this direction is a kind of compression, this matrix is the sort of decompression matrix. So it's given to you by physical theory, because it's the equations of the physical theory that tell you how the different quantities are related. So this, in a sense, encodifies part of the physical theory. Decompression matrix. I mean, in a sense, you can sort of see where I'm going because I won't have time to get all the way there. If you can somehow compress the entire theory, then the decompression matrices that you have as a consequence really represent the theory. Because what the theory does is it's about, what a physical theory does is it relates physical quantities by physical compression. So if you understand how the compression or how the decompression works, then in a sense you specify the theory fully. So that's the situation for one region.
So if you allow all possible measurements rather than just discrete set, you get infinite dimensional vectors then?
Yeah, so because I'm an operationalist, as far as this work is concerned, you could never, in any real experiment, have that kind of resolution. So you have a finite set of measurements. But you could be very, very long list. So alpha.
But does the compression somehow grow with the number of, like, as you go through like a continuum
Well, so in quantum,
you get some finite dimension to this compressed vector?
yeah, so I think in quantum theory, for example, you can look at the compression for, say, a single qubit. And just in the simplest case where you're just looking at the normal time forward evolution, you only need to have n squared real numbers or probabilities to specify the state of a qubit, even though you can calculate an arbitrarily large number of probabilities from a qubit.
So the same thing applies in this case.
Exactly. Yeah. So in fact, this more general case came from thinking about that simple case. So I call what I do there first level compression. So this is second level compression. So second level compression applies when you have a region which is regarded as being made out of two or more regions. So we have a region that's regarded as being composite. So there's a region that's regarded as being composite. We're thinking of R1 and R2 as being disjoint. So we can do the same kind of stuff. Our set of alpha labels is just going to be the Cartesian product. So you have things like that. Then we're going to have some omega set, which is a subset, of course, of the set of all possible labels. And then there's a theorem that you can always choose. So this is a theorem. It's a simple theorem. It's a useful theorem. You can always choose the omega set for this composite region from the product, from the Cartesian set of omega 1 cross omega 2. So you can think of two special cases here. So one special case is where this set is just equal to the Cartesian set. And that's a kind of trivial case. In the case of quantum theory, that corresponds to the tensor product. And then you can think of the other situation where this is a proper subset. And in the case of quantum theory, an example of where this is a proper subset is composition. And what you can do is you can quantify the, because in a sense what you have here is when you put two systems together, if this is a proper subset of this, then you have some additional physical compression for the composite region over and above the physical compression for each of the two regions separately. And you can quantify that in the same way, I won't go into the details, using a certain matrix. So this matrix, the labels here are in the Cartesian product set, and the labels here are in the omega 1,2 set. And so this matrix quantifies the physical compression. So when you write down the causaloid product, it's this matrix that you call on. But what's interesting is the product is basically the same, it has the same mathematical form, regardless of where these two regions are. Of course, the matrix itself may differ depending on where the two regions are, but the mathematical form of the product is the same, regardless. And actually, if I can write this down. So you can see it's just this kind of, I guess this is a bilinear product. So this is how the causaloid form is defined. And so all the different products that you have in quantum theory, the composition product, the tensor product, even the question mark product, are special cases of this particular product where you choose matrices accordingly. And not just those cases, but also if you want to combine any two regions, you might want to, you go back to having a quantum circuit, whatever. You might want to combine this region with this region, and you can just take the causaloid product between the appropriate operators. So you can do any kind of combination of that nature that you want. And then these vectors tell you whether the probability is well defined, and if they are, how to calculate them. And maybe I'll finish with just one general remark. So there's a concept that comes out of this which I think is nice. So I call it F locality. So F locality, F stands for formalism, or formulation. F stands for formulation. So this is a property not of a physical theory as such, but of the way in which the physical theory is formulated. So you can look at the formulation of any given physical theory and say whether it's F local or not. And so a theory is defined to be F local if, in making statements or making predictions about a given region of space-time, so if in making predictions about an arbitrary region of space-time, R1, we only need to refer to mathematical objects. if you're making a prediction about region R1, you only need to refer to mathematical objects that are themselves defined in R1. So I think this is a useful constraint to put on the formulation of a theory. I think it's a very nice thing. It says that you shouldn't be looking at regions that aren't part of the region that you're trying to make a prediction for. You can see that standard pictures of, in which quantum theory is formulated are not F-local. So for example, if you have a time evolution picture, imagine you want to make a prediction concerning this region of space-time. And you have a time evolution, then you have to have some state that's defined before, and you have to evolve it till afterwards. And then you use the mathematical machinery, the theory, to say what the probabilities are concerning these regions. But you have to refer to intermediate places which aren't part of your original region. The same is true, of course, of a histories approach. If you take a histories approach, then you have to refer to mathematical objects that are defined on all of space-time. And then you specialize down to the particular part of space-time that you're interested in. And also, if you think about it carefully, even if you have local equations, like in the case of Maxwell or Einstein equations, it's also not F-local, at least not obviously so. So I'll stop there.
Thank you. So I think rather than taking questions now, we should have a...
I have a quick comment.
Yeah.
Right to answer.
Okay.
It's going to take 1 minute. And it's very compelling. So you've got a cone here, yeah? You've got F here and G there. And this is what you identify with the idea of composing and these lines, yeah?
Sure.
And you've got tensor and you've got composition. Yeah? You've got these things. Saying you don't like them because you don't like the separation in, for example, having here F in a diamond, having there G in a diamond, or having maybe F here and G there. Yeah? So you don't want the fact that you a priori have to make a choice like that. Huh? Yeah? See, the boxes there. And instead of scrapping these, I'm just going to add two things. This and this. And if I now can find some blue chalk, then we can do this. And maybe there's some other influence. Maybe there's some other influences going on. We don't care. Yeah? We got here this, and then we got this. Ah, it's probably the wrong one. Yes. This, and then this. And then we got here this and this. And they're all equal.
So the product itself is the same, but now you have additional structure.
I've got additional structure, and this additional structure sort of makes...
So you only have one now, you only have one thing here.
No, it's still there. It's just by adding these two, you actually undo what you thought was imposed by these things. So adding this guy actually takes away your causal dependencies which you felt were imposed by this form.
Okay.
So you can just mix them around. So in a way, adding these two things which you call quantum structure actually like liberates your causal structure. And you can just put them wherever you want. And this thing as a whole, we could just write down as causaloid product between F and G.
Okay. I have to think about this. I mean, the contrast is you have these pieces of structure. I have this one.
Yes.
Just one thing I need to
So basically, you've got your F and your G, and then by your construction, you actually find the lines and the correlations between them. There is no a priori spatial connection there. But I think this is exactly what this compact closure captures, the fact that before and after don't matter anymore. Because it just, whenever there is a connection, but whether it is a space-like connection or a time-like connection, it really doesn't matter.
What if it's not space-like or time, but indefinite?
Well, in a sense, it's nothing of the two a priori. So you see, it's a choice you can make, it's a choice you can assign how you want to interpret this on a page. But what actually matters is just the wires between things. And
There's a maybe interesting mathematical question to take one formal framework and the other formal framework and see whether they're equivalent or one can achieve
well, I
more.
think you would be able to specify this then more to get. Definitely, they are not incompatible. That's what I'm showing you.
I mean, I don't quite see, because I still think, I think there are situations that one could model with this, that one couldn't model with this structure, because this seems to have more definite sort of causal structure built into it, even if you lay it on top in
See, I reverse the order between F and G, completely.
So that is a definite mathematical conjecture which can be considered
this we can
and answer yes or no.
Yeah. So there's the parameter lambda, right? Lambda is an object which is you're not assuming a description of lambda. You let some lambda exist.
Yeah, to make this, because lambda, the particular lambda that's called upon the matrix to influence on a particular region requires a lot of real numbers to specify the matrix, whereas you've just got a kind of discrete structure.
Yeah,
so
sure.
You
have to specify. No, this is a very abstract model. I'm just showing this. There is no contradiction there.
Okay.
With respect to assignment of spatial temporal structure, because adding these cups and these caps actually makes it very flexible.
I mean, I agree it makes it more flexible, whether it can go with the full.
As one of the models of this, we'll learn something which will have lots of real numbers as scalars. So it may be a special case of that framework.
So what is lambda then?
Oh, sorry, I never actually really said what. I mean, lambda is something you can call on to get any of these objects.
But where does it come from?
I mean, then I need another 20 minutes or half an hour. I shouldn't take
right.
too much time. Yeah.
Well, let me make it a very short question then. Is the rest of your theory predictive of lambda in some cases?
So if you give me a particular theory, and I'm clever enough, then I can calculate what lambda is. So in the case of quantum theory, I can tell you exactly what lambda is. There's still work to be done there in general, but
Okay, thanks again, Lucien. I still think we should take a 5-minute break. So we'll reconvene at 4:20. 4:15 now.
Obviously what you said. Turn that off. Put this off.